Hey everybody, this is Larry. This is me going over day 23 of the February Leetcode challenge. Search a 2D Matrix 2. Hit the like button, hit the subscribe button, join me in Discord. So today I'm going to do this out a little bit of a funky order. I actually spent some time solving this already, and I actually came up with two solutions that are kind of, well, one solution that's good, and then a couple of naive solutions. I actually go over all the details later, so if you want to fast forward to the wrong Larry, you could do that. But one thing that I did forget was the M plus N algorithm, and I feel like this is where you should have it, so I'm going to go explain this instead. So while you do that, hit the like button, hit the subscribe button, join me in Discord or whatever you like. I don't know if I said that already, but the key thing to know about this format, and I actually did know this, but I forgot to, I didn't incorporate it in a good way. But let me draw some ASCII art here, and I actually talk about different ways to kind of, analyze this. So definitely, if you have time, go watch the rest of the video. But if not, this is going to be me going over the answer directly and coding it really quick, ideally. But yeah, but the idea is that, okay, so if you look at any cell, what does this tell you, right? That means that if the target is greater than this, then if the target is, well, let's do the other way around first. If the target is smaller than this, that means that this rectangular corner, okay, that's a little bit awkward, but everything to the left of 16 and then 16 and higher, so basically this, these four numbers, and these four numbers. If the target is less than 16, then you know that it's in that quadrant, right? And that's the only invariant that you need. You might use this invariant to come up with if this is a square matrix, I come up with a log m plus log n algorithm or something like that. Or I guess that's log n if this is a square matrix. But since this is not in this case, it's a square matrix, but in the general case, this is not. So what I would do is, looking at that invariant, what does this mean, right? That means that you get to draw boxes, and then try to eliminate it, one portion at a time. So let's start with the target. Let's say 20, right? So your box would be here, and you look at 15. 15 is too small. That means that it's not going to be any of the numbers in this box. So then we go down. And then 20 is still bigger. That means that it's not going to be any number, because 19, that means that it's not going to be anything to the left or upper. So then we can eliminate these, all together, right? And then here is 22. 22 is smaller, so that means that we know that it has to be in this quadrant, all right? So then we could eliminate everything. Then that means that we can eliminate everything to the bottom of this, because everything to the bottom of this is obviously bigger than the number, and everything to the right, I guess, but technically as you move to the left, it's going to eliminate. So here, we have 20, so we'll remove this because we know that that's true. So now we're at 16. Again, we have 20, so 20 is bigger than 16, we could eliminate this row. And we're at 17, 20 is bigger than 17, so we could eliminate this row because we know that everything to the left of it is going to be smaller. And then now here, we just, there's only one row left, so the idea is the same, but you basically go left, 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 and then you're like, oh, no more 20, so this is sad, and then I return. So that's basically the idea, and because you remove either one column or one row at a time, this is going to be m plus n, which is sublinear, because linear is m times n. And I go over kind of in my full explanations, I go over the more naive explanations, but that's basically how I would solve this problem. It's just eliminated one at a time. But that's how I would solve it now, because I don't know, when I was solving it the first time, I forgot about this recurrence, and I was trying to go from the upper left corner instead, and I played around with binary search. Again, I'm not going to explain it because you can watch that video or later in the video if you like, and you can fast forward to that. But for now, we're going to implement this. So then we start with, okay, rows is equal to the length of matrix. Let's see, okay. Column is equal to the length of matrix of 0. And then now we can start with, let's just start with x is equal to 0, y is equal to columns -1, and then we go. And then we go from, to the corner. So while x is less than rows and columns is greater than equal to 0, we check, right? If matrix of xy, so what did we say? If this is greater than, well, if this is equal to target, we just return true. So let's get that out of the way. If matrix is bigger than the target, that means that we have to move down, right? As we said, because we just eliminate everything to the left of that, it's going to be true. So yeah. And then else, if matrix of x plus y is less than target, I guess we can just do an else here too, right? Obviously doesn't matter. That we subtract 1. And that's basically it. And then otherwise we return false. And yeah, that's basically all I have. I would say, so, my live self, I actually forgot about this algorithm, so I actually looked at the form, but I didn't look at it that much. I'm like, oh, there's a linear algorithm. And as soon as I knew that there's a linear algorithm, I was like, because I always, there are a couple of variations of this problem, and I always forget, I always mix them up, which one is which, to be honest. But yeah. Oh, whoops. Typo. That's interesting. Why? That's a little sad. But we could debug this real quick. We start 15. And then did I get the signs wrong? If this is bigger than target, then, oh yeah, I got the wrong one. I mixed them up. That's pretty much the only mistake you can make on this farm, and I made it. So yeah. Okay, let's give it a submit. Cool. And of course, this is going to be O of m plus n, because as you can see, for each column we only move right once at most, and then for each row we only move down once at most. So that's going to be m plus n, and of course this is all one space because we don't really we only use a couple of variables here, right? So yeah, that's basically all I have. I don't have anything more to say. I think I added more context on. You can watch the video where I go over some of this, but I think this is. I don't like this problem per se, and I don't really remember it that much, and that's why this is a long video. But I would say that people keep on telling me that they get this on interviews, so maybe practice it enough. I'm okay. And on competitive, I would definitely either do, just look at every cell, or do a binary search or something like that, or like m times n binary searches. But yeah, that's all I have. You could watch me solve it for the first time next, and it's going to be a little bit weird because I'm just going to do the intro again. But anyway, you could watch that next. Hey everybody, this is Larry. This is day 23 of the February Leetcode Daily Challenge. Couple of days more to go. Let's get to it. Search a 2D matrix 2. Hit the like button, hit the subscribe button, join me on Discord. Let me know what you think about this problem. Write an efficient algorithm. Yeah, okay. I was going to write an inefficient one, but you got me. Search for a target value. Okay, it's fun price. Each row is sorted from left to right. Each column is sort of from top to bottom. So this is a standard-ish, and it's not standard. And I don't even know if you should know it. It doesn't come up that much, and I always mess this up. But people keep on telling me that it comes up a lot. So anyway, so so you just search for a number. Okay. So the obvious thing is that if you look at every element, it's going to be linear time. Where linear is every cell, m times n, right? And yeah, ideally you can do better than that. Let's see. So this is sorted. Okay, so it's actually sorted in both directions. So that means that you can do some, do some funky binary search. I think there are naive. There are other slightly less naive algorithms, but still naive ones are like, m log n or n log m. for binary search on each row. I think there's an m plus n one. Am I thinking of a different problem? That might be, to be honest, where you're forced to. Oh, am I thinking of the right one? I don't know, but yeah. And I'm going to try to see if I could come up with this one. Is there? I mean, given the n and m is 300, I wouldn't worry that much about it, to be honest. But with respect to like on a contest, I would just do something naive. But it is, you know, as a habit of by naive, I mean probably n times m. But also, you know, this is definitely, if you're here practicing, you should try to do a little bit better, because that would not be that would not be acceptable in an interview, assuming that they're like, okay, you can write for loops. That's not impressive. Okay. I would say this is also one of those standard problems that I never get I always forget how to do it exactly. So let me see if I could reconstruct it from my invariants, if you will. So we can do a binary search on. Can we do a binary search on? Well, okay. Let's think about what it means, right? Let's say that, you know, we're looking at the cell 3. What does that mean? That means that all the numbers that are under it is no good. And all the, not even just under it, like to the right and under it are no good, right? Because that means, wait, is that true? No. What am I talking about? Okay, no. So if we're looking at, can we do some quadrant stuff? So let's say we have the 9. Now I'm just trying to do something funky. Let's say we have the 9. We can eliminate. Can we eliminate quadrants? Yeah, I mean, we can eliminate 1/4 at least, but that's not really that ideal. Or not sufficiently ideal, maybe. Because you can do the recurrence of like 3/4 plus, you know, 3/4 of that and so forth, right? So that's not a good series to sum up. Is there a linear of 1? Man, I'm really bad at this, so I hope y'all are enjoying it at home. Let's see. Okay, let's say we start at 1, right? Then do we want to go to the 2 or the 4? Are we looking for 5? I guess it. Well, we go to the 2 and then we go for the 3, then it doesn't really make sense, right? I feel like there's a walking algorithm, but I don't remember, which makes it n plus m, but I forget how that goes. Do we want to get the bigger number or the smaller number? Well, what does that mean to go to the right, right? If it goes to the right, it means that it cannot exist in all the things to the left, which is not true if we are going to do a walking algorithm, because in theory, and I'm just not drawing this, let's play around with matrix here. Let me put it here with some ASCII art, if you will. But you can imagine that what I just said was not true. So, if that's the case, is it only n times log m? Because, you know, let's say we put 5 here, then I mean, I know that this is unique, so okay, let's just search for another number then. Okay, let's make this some x number. Let's make it 5.5. And then for 5, if we put it here, then obviously we have to go straight down. But I forgot what it was, 10. But if we put it here, we obviously have to go here to the right? So there's no decision that. So I think by contradiction, maybe, that I don't think there's an n plus m algorithm, but I could be wrong. I don't know if that's a hard proof for me, but it's just that, you know, making a decision, you don't if you only look at the immediate adjacent characters, it doesn't tell you where the 5 could be, because it could be here or here, right? As we said, it could be here or here. Yeah, is there some diagonal thing that we can take care of? I don't know. What was this searching for? 20? I've been talking a lot for a problem that I haven't even written any code yet, but 20. So where you got 1, and then you go to the 5 to kind of. What is the 5? So what does a 5 mean? 5 means that all the numbers to the left. Okay, I could buy that. And then 9, and then 17. Right? I could buy the diagonal argument. But what does that mean for me, right? And you could binary search on the diagonal from what we just said. Basically, the right diagonal. What I'm just saying is that diagonal means that everything to the quadrant is false. And then you could do. So you do a log of n plus m plus n plus m, which is going to be n plus m, right? Is that true? I guess that's kind of an n plus m algorithm. So basically, I don't know if I said that clearly, but basically my idea right now is that we can binary search on the diagonal, right? Because I forget what it was, 10. Let's make this, I forget what it was, 8 now. It's like, it doesn't really matter if it's 7. Basically, we could binary search on the diagonal because we know that 1 is 1, but 5 means that everything to the left and up and everything in between are going to be on it's going to be smaller than that, right? So we binary search, and that means that this is strictly true going all the way go. So then we can binary search. Oh, that's not diagonal. You can binary search at the diagonal to get the row and the column that you're in, that the number should be in, if it is in there, and then you could just do a linear search n plus m on that row plus column. And because that's log of n plus m, that's going to be dominated by n plus m. Can we do better? Yeah, I mean, the answer is yes, because now that you have the row plus column, then you could just binary search on that. So that means that it's going to be log of n plus m, or log of n plus log of m. Okay. I think I'm convinced. I don't know if I could prove this, so I guess we'll just have to prove it by AC a little bit. No, I mean, I'm relatively okay. I'm happy that I came. This is a long video, and I apologize, but I think we've been playing around it properly. So I think I'm going to try it. I mean, I don't know if it's right. I'm relatively sure, but I don't know that I missed anything. So that's what I'm going to do. We're going to go to So what I said assumes that this is m times n, and I think it still works without n times m, but it's just a little bit more tricky, because then now, let's say, I mean, in a very basic case, you have, let's just say this, right? Then we can't really binary search on the diagonal. Well, we binary searched here or here, and then what happens if this is here, right? If this is here, that means that it still could be in all these other ones. So, okay, so what I said is true for a square matrix. So, because, now we have to take care of all these other O's after we search those two. So that is not good enough, because then you have to keep going. Right? Is there a way to kind of take advantage of that as well? I mean, the answer is yes. You can do, repeat, do the same logic with repeat doubling. I mean, I said binary search, but you can also do repeat doubling or whatever, but it's the same idea. And you could definitely do it with, things, but it's just, the complexity is just really hard. not really hard, but there's a lot of off by one potentials and annoying things. I think if this is a way more interesting problem with this m is equal to n, only because of that reason. Otherwise, then you have this thing, and then what do you do? Let's see. Because I mean, you could also let's see. Yeah, I don't know. I was excited to implement this, and then I realized this edge case. Or it's not an edge case. It's probably all the other case other than the perfect case. But I mean, you can do it, but it's there's a lot of yuckiness. So I'm just going to do the regular m times log n one, and a little bit sad because that's a cool algorithm. Can I really take advantage of it? No, I don't. Yeah, I don't know. I am a little bit tired though, because I do these at 3 a.m. So I'm just going to do the naive algorithm, and then we'll see. And then we'll go over the solution together. I think some of it is just me being lazy, to be frank, and I apologize for that if you're staying up for that. But I hope I gave you at least ideas to my insights as I go through this. But you know, we'll go over the solutions together. We'll read the forums, the solutions, or whatever, and then we'll play around with it. Or maybe I even have done it before. I don't know. Yeah, let's go. So for row in matrix, bisect dot bisect left. Row of target, if row of index is equal to target, return true, return false, right? So that's basically what I would do during a contest. And as you can see, this is done very quickly. Like, I know that I talked a lot, but you know, if this was a contest, I definitely would have done this already. And this is what I would submit, especially if this was a Yeezy or something, or maybe even just a folder, really. But maybe I would have gotten the wrong answer though, because I forgot to check one thing. But well, I mean, that's why I run the tests. What? Oh, whoops. A little bit rusty right now. Mostly from all the talking, probably. Alright, well, let's just go submit. Oh yeah, so this is going to be m times n, m times log n, or I mean, I'm just going to say m times log n. You could actually make it a little bit better by transposing the matrix, or something like that. Maybe not actually transposing it, but you know, basically binary search the dimension that is longer. But I trust you know how to do it if you need to. But yeah, but this is going to be all of, I don't know if this is m times log n or n times log m, whatever, but same idea. So basically, for each row, you have log c. Maybe that's a better way of doing it. You can swap the pointers if r is greater than c. If r is equal to c, we have a beautiful idea. And of course, this is all one space, because we don't really do anything else, right? Okay, let's take a look. The solution's locked. Let's go discuss, see if anything good. Anyone got anything good? Oh, there's an m times m solution. Yeah, or m plus n solution. I thought that I couldn't do this. Is this true? Top. Oh, you have to do it from top right corner. Maybe I was a little bit off. Okay, let's go back. I didn't really read the entire thing. But I mean, I already had the idea. So, ooh, what did I click on? So, 15, 11. Why is that true? I guess this is the same idea that I had, except for this is much fancier with the binary search of try to figure out what quadrant that the thing is in, and the invariant in this problem is that is that yeah, let me actually go over it. You know what? I'm gonna actually, okay. If you're watching this, this is gonna be in a weird order. But I'm gonna record this and then put it in the front. So I mean, if you're watching this, it's explaining to you will be really weird. But anyway, I'll see you later. So I'm just gonna do my goodbyes. I'll see you later. Thanks for watching. And yeah, hit the like button, hit the subscribe button, join me on Discord, and also just take care of yourself, take care of others, have a good day, and you know, have the good mental health. And I'll see you tomorrow. Bye bye.